For over a century, scientists have dreamed of a material that carries electricity without losing a single watt to resistance, at room temperature. No freezers, no exotic pressures, just plug and go. It's been called the holy grail of physics, and for just as long it's eluded us. But now artificial intelligence has done something no human research team could do alone. It scanned through an almost limitless universe of possible materials and pointed directly at candidates nobody had ever tested. What happened next stunned even the researchers. To understand why this matters, you have to understand just how strange superconductivity really is. Ordinary electrical wires waste energy every single time current flows through them. That waste shows up as heat, and on a global scale it adds up to a staggering amount of lost power. Power plants generate electricity, send it across transmission lines, and by the time it reaches your home, a meaningful chunk of it has simply evaporated into the air as wasted heat. Now imagine a material that didn't do that. Imagine wires that carried electricity with perfect efficiency. No loss, no waste, no heat bleeding away into nothing. That is the promise of superconductivity, and it is not science fiction. It already exists. The catch, the one that has haunted physicists since the phenomenon was first discovered in 1911, is that superconductivity has almost always required brutally cold temperatures to work. The first superconductor ever found was mercury, cooled down to nearly absolute zero, the coldest temperature theoretically possible in the universe. At that temperature, something remarkable happened. The electrical resistance of the mercury didn't just drop, it vanished completely. For decades, nobody could fully explain why. Then in the 1950s, a trio of physicists named Bardeen, Cooper, and Schrieffer worked out a theory that finally made sense of it. At extremely low temperatures, electrons in certain materials stop behaving like isolated particles, bouncing around and colliding with obstacles. Instead, they pair up, forming what are now called Cooper pairs. These paired electrons move through this material in a strange coordinated dance, slipping past the atomic lattice without scattering, without losing energy, without resistance. It's one of the most beautiful demonstrations of quantum mechanics, operating at a scale we can actually observe and use. But there was a problem baked into that very theory. The pairing of electrons that made superconductivity possible was itself fragile. Heat disrupts it. As temperature rises, the atoms in a material vibrate more violently, and those vibrations shake the delicate Cooper pairs apart. For decades, this seemed to be an iron law of nature. If you wanted superconductivity, you needed cold, and not just cold, but extreme cold. Temperatures only reachable with liquid helium, hovering just a few degrees above absolute zero. That kind of cooling is expensive, complicated, and completely impractical for everyday use. You are not going to run liquid helium through the wiring in your house. Then, in the 1980s, everything changed, at least a little. Researchers discovered a new class of materials called high-temperature superconductors, ceramic compounds that could superconduct at temperatures reachable with liquid nitrogen instead of liquid helium. That might not sound like a huge leap, but liquid nitrogen is dramatically cheaper and easier to produce than liquid helium, and suddenly, superconductivity felt within reach of practical use. Hospitals began using superconducting magnets in MRI machines. Maglev trains started floating on superconducting tracks in Japan and China. Particle accelerators, like the Large Hadron Collider, relied on superconducting magnets to bend beams of particles traveling near the speed of light. But even these high-temperature superconductors still required serious cooling, well below anything close to a comfortable room temperature. The dream of a superconductor that worked without any special cooling at all, one that simply functioned under normal everyday conditions, remained stubbornly out of reach. This is where the story gets interesting, and where the sheer scale of the challenge becomes clear. Finding a new superconductor is not like tweaking a recipe in a kitchen. It involves combining elements from across the periodic table in different ratios, different crystal structures, different arrangements of atoms, and testing whether the resulting material exhibits this strange zero-resistance behavior at any usable temperature. The number of possible combinations is almost incomprehensibly large. Researchers have estimated that if you tried to test every plausible combination of elements and structures by hand, one at a time in a lab, it would take longer than the age of the universe to get through them all. And yet, despite that impossible odds, scientists have discovered more than 7,000 superconducting materials over the past century, mostly through a combination of educated guessing, a painstaking trial and error, and frankly, a fair amount of luck. That is the world artificial intelligence walked into, and it did not walk in quietly. Instead of testing materials one by one in a physical lab, researchers began training machine learning models on the entire known history of superconductivity. Every material ever tested, every crystal structure ever recorded, every known relationship between atomic composition and electronic behavior. The AI systems learned to recognize patterns that human researchers had missed, subtle correlations between how electrons arrange themselves in certain geometric lattice structures, and whether that arrangement is likely to produce superconductivity. One especially promising pattern involves something called a Kagome lattice, named after a traditional Japanese basket weaving technique that produces a repeating pattern of interlocking triangles and hexagons. When electrons move through a material with this specific geometric arrangement, something unusual happens to their energy levels. They form what physicists call flat bands, regions where large numbers of electrons can occupy nearly the same energy state at once. This traps electrons together in a way that appears to encourage the very pairing behavior that drives superconductivity in the first place. An international team of physicists working through a global research collaboration known as the Super-C Consortium decided to put this idea to the test at scale. Led by physicist Päivi Torma at Aalto University in Finland, the team combined machine learning with detailed quantum physics calculations, using the AI not to replace human expertise, but to dramatically narrow the search. Instead of researchers guessing which of the near-infinite combinations of elements might be worth testing in a lab, the AI system sifted through the possibilities computationally, ranking candidates by how likely they were to exhibit the electronic conditions associated with superconductivity. It flagged the most promising structures, the ones most likely to succeed, and handed that shortlist to the human scientists. Two materials rose to the top of that list. They're called YRU3b2 and LuRu3b2, compounds built from yttrium, lutetium, ruthenium, and boron arranged in that same Kagome lattice pattern that had shown such promise in earlier calculations. Neither material had ever been synthesized before. Neither had ever been tested. According to conventional wisdom and decades of trial and error intuition, there was no strong reason to expect either one to be a superconductor at all. But the AI's calculations suggested otherwise, and the team decided to find out for certain. That's where the story moved from computer simulations into a real laboratory. Researchers at Rice University in Texas, led by physicist Emilia Morosin, took the AI's predictions and set out to actually synthesize the materials, combining the raw elements under carefully controlled conditions to grow the exact crystal structures the models had predicted. This is not a trivial process. Building a new material atom by atom, coaxing it into the precise crystalline arrangement that theory says should work is a slow, delicate, and often frustrating process, even when you know exactly what you're aiming for. But the team succeeded. They created both compounds in the lab, and then came the moment of truth. They cooled the materials down and tested whether electricity really would flow through them without resistance, just as the AI had predicted. It worked. Both materials exhibited genuine, measurable superconductivity. YRU3b2 became superconducting at a critical temperature of about 0.81 Kelvin, and LuRu3b2 followed close behind at 0.95 Kelvin. Now, to be clear, those numbers are still extraordinarily cold, far colder than anything usable in your everyday life, colder even than the coldest recorded winter night anywhere on Earth. This is not, on its own, a breakthrough that puts room temperature superconductors in your walls tomorrow. But that misses the actual significance of what happened here. The discovery wasn't really about those two specific materials. It was about proving that this method, using AI to predict which materials will superconduct before ever stepping foot in a lab, actually works in the real world on brand new, never-before-seen compounds. As Torma put it, researchers have identified more than 7,000 superconductors over the decades, but mostly through serendipity, through accident and stubborn persistence. This was the first time a coordinated AI-driven search successfully predicted new superconductors from scratch and then confirmed them experimentally. Think about what that means for the pace of discovery going forward. If it once took years or even decades of trial and error to stumble onto a single new superconducting compound, an AI can now screen thousands of candidate materials computationally in a fraction of that time, flagging only the most promising handful for actual physical testing. The entire discovery pipeline compresses dramatically. Instead of blindly searching a haystack the size of a planet, scientists now have a map, one drawn by an AI system that has learned the hidden patterns connecting atomic structure to electronic behavior. The Super-C Consortium has stated its ambition plainly. They aim to identify a genuine room temperature superconductor by the year 2033. A decade ago, that kind of timeline would have sounded almost delusional. Today, with AI accelerating the search, it suddenly sounds like a legitimate, achievable target. But the AI-driven discovery of YRU3b2 and LuRu3b2 is not the only strange and unexpected superconductor making headlines right now. In fact, physicists working independently of this AI research have been wrestling with a material that seems to break the rules of superconductivity in an entirely different way. It's called uranium ditelluride, or UTe₂ for short, and it was first discovered back in 2019. From the moment researchers began studying it closely, it was clear that this was not an ordinary superconductor. Most superconductors, even the unconventional ones that don't fit neatly into the original Cooper pair theory, still tend to follow somewhat predictable rules about how magnetic fields affect their behavior. Typically, strong magnetic fields destroy superconductivity. They rip apart the delicate electron pairing that makes zero resistance possible in the first place. UTe₂ doesn't play by that rule at all. Instead, researchers discovered that UTe₂ exhibits something called re-entrant superconductivity. As you increase the magnetic field applied to the material, its superconductivity does initially weaken, just as you'd expect. But then, at extraordinarily high magnetic field strengths that would obliterate superconductivity in almost any other known material, UTe₂'s zero resistance state doesn't disappear. It reappears. It's as if the material shrugs off the magnetic field, finds some entirely new pathway to maintain its strange electron pairing, and keeps conducting electricity without resistance anyway. Physicists at the Institute of Science and Technology Austria, working alongside collaborators internationally, published new research on this phenomenon, revealing giant transverse magnetic fluctuations occurring right at the edge of this re-entrant superconducting state. In plain language, they found that something dramatic and previously unrecognized is happening to the electrons inside UTe₂ at exactly the boundary where ordinary superconductivity should collapse under magnetic pressure and instead transforms into this bizarre hidden state that persists at fields where nothing should be superconducting at all. Understanding why this happens is not just an academic curiosity. It goes to the very heart of unconventional superconductivity, a category of materials that simply refuses to be explained by the original Cooper pair theory that worked so well for conventional superconductors like mercury or lead. In conventional superconductivity, electrons pair up because of interactions with vibrations in the atomic lattice, called phonons. But in unconventional superconductors like UTe₂, and like many of the high-temperature ceramic superconductors discovered in the 1980s, something else appears to be driving the pairing, something connected to magnetism itself rather than lattice vibrations. Physicists call this a triplet pairing state, as opposed to the more common singlet pairing found in conventional superconductors. In a triplet state, the paired electrons align their spins in the same direction rather than opposite directions, which is part of why these materials can survive under magnetic conditions that would destroy conventional superconductivity outright. This brings us to yet another jaw-dropping development in the superconductor world, one that researchers have described as potentially the holy grail of quantum computing itself. Scientists studying an alloy called niobium-rhenium, or NbRe, believe they may have spotted direct evidence of triplet superconductivity in action, a material capable of transmitting not just electricity, but electron spin with zero resistance. If confirmed, this would be enormously significant, because quantum computers don't just need electricity to flow efficiently, they need to preserve incredibly fragile quantum information, encoded in the spin states of individual particles, long enough to perform meaningful calculations. Today's quantum computers are notoriously unstable. They require extreme cooling, elaborate error correction schemes, and even then, the delicate quantum states they rely on tend to collapse or decohere within fractions of a second. A material that could transmit spin information without resistance and without that same fragility could become the literal backbone of a new generation of quantum computers, ones that are more stable, more energy efficient, and dramatically more scalable than what exists today. Early experiments on NbRe suggest it behaves unlike any conventional superconductor scientists have studied before, hinting at exactly this kind of triplet pairing behavior. If further research verifies these results, NbRes could become a cornerstone material for spintronic devices, an entire branch of electronics built around manipulating electron spin rather than just electron charge, opening the door to faster, more efficient computing architectures that barely resemble the silicon-based chips inside your phone or laptop today. So where does this leave us? With AI-discovered Kagome lattice superconductors, a magnetically defiant uranium compound that seems to break its own rules under pressure, and a possible triplet superconductor that could reshape quantum computing itself. It leaves us at a moment where multiple independent lines of cutting-edge physics research are converging on the same fundamental goal, unlocking materials that conduct electricity, and in some cases, quantum information itself, with zero loss, under conditions we've never been able to achieve before. The stakes here go far beyond academic curiosity. Consider the sheer scale of energy wasted globally every single day due to ordinary electrical resistance. Every transmission line, every data center, every electric motor, every appliance plugged into a wall socket loses some fraction of its energy to heat, because the materials carrying that electricity are not perfect conductors. Estimates suggest that a meaningful percentage of all electricity generated worldwide is lost this way, simply bleeding off as waste heat before it ever reaches its intended use. Now, imagine a world where the materials inside power grids, inside computer processors, inside electric vehicle motors, inside the servers powering artificial intelligence itself could conduct electricity with zero resistance at room temperature, without any exotic cooling systems required. The scale of energy savings would be almost impossible to overstate. Data centers, which already consume staggering and rapidly growing amounts of electricity to power the modern digital economy, and particularly to power AI systems themselves, could become dramatically more efficient. The irony is almost poetic. Artificial intelligence, one of the most energy-hungry technologies ever created, might end up being the very tool that unlocks the materials needed to make computing itself dramatically more energy efficient in the future. Beyond energy savings, there are entire categories of technology that a practical room temperature superconductor would fundamentally transform. Maglev trains could become cheaper and more widespread, no longer requiring expensive cryogenic cooling systems to keep their superconducting tracks functional. Medical imaging technology like MRI machines could shrink in size and cost, making advanced diagnostic imaging more accessible to hospitals and clinics that currently can't afford the infrastructure required to maintain superconducting magnets near absolute zero. Fusion reactors, which rely heavily on powerful superconducting magnets to contain superheated plasma, could become more efficient and less expensive to build and operate, potentially accelerating the long and difficult path toward viable fusion energy. And quantum computers, which currently require some of the most extreme cooling systems ever built by human engineers, colder even than the vacuum of deep space, might one day operate under far less extreme conditions, making them dramatically more practical to build, deploy, and scale. It's worth pausing here to be honest about where the science actually stands right now, because it's easy to get swept up in the excitement of headlines proclaiming impossible breakthroughs. The materials discovered through the AI-driven search at Aalto and Rice University, YRU3b2, and LURU3b2 are still superconducting only at temperatures colder than anything found naturally on Earth. They are not, by themselves, the room temperature superconductor everyone has been chasing for over a century. What they represent instead is proof that a new method, one driven by artificial intelligence and quantum geometry calculations rather than trial and error, can successfully predict genuinely new superconducting materials before anyone ever synthesizes them in a lab. That is a profound shift in how this kind of science gets done. Similarly, the strange behavior of UTe₂ and the possible triplet superconductivity in NbRe represent important steps toward a deeper theoretical understanding of unconventional superconductivity, the kind of understanding that will ultimately be necessary to design a practical room temperature superconductor on purpose, rather than stumbling onto one by luck. This is really the heart of why this moment feels different from the decades of superconductor research that came before it. For most of the last century, the search for new superconductors has resembled searching a vast, dark room by feeling around blindly, occasionally bumping into something useful. Artificial intelligence has effectively turned the lights on. It hasn't found the exit yet, the room temperature superconductor that changes everything, but it has revealed the shape of the room, the patterns connecting atomic structure to electronic behavior, the geometric arrangements like Kagome lattices that seem to encourage superconductivity, and the theoretical frameworks needed to explain why materials like UTe₂ defy conventional expectations in the first place. Every one of these discoveries adds another piece to an increasingly complete map, and a research team pursuing a goal as ambitious as achieving room temperature superconductivity by 2033 needs exactly that kind of map to make real progress on a timeline once considered wildly unrealistic. This AI-driven approach to superconductor hunting isn't limited to a single research group either. At Johns Hopkins University's Applied Physics Laboratory, another team has been pursuing a strikingly similar mission through a project called Mithril. Working alongside leading quantum materials researchers, including chemistry professor Terrell McQueen, the team set out to answer a deceptively simple question. If there are already thousands of known superconductors, and scientists understand quite a lot about the compositions and structures that tend to produce them, could an AI system be trained to systematically sample the enormous space of untested compositions and flag the ones most likely to be genuinely new superconductors, rather than leaving that search to chance? The reasoning behind this approach gets at something fundamental about the difference between human and computational problem solving. Human researchers, no matter how experienced, reason primarily from what is already known, drawing on intuition built from years of study and observation. Computers, on the other hand, can be trained to systematically explore the unknown, methodically working through possibilities that no single human mind could ever hold in view all at once. That distinction may end up being one of the most consequential shifts in how scientific discovery happens across the next several decades. Of course, none of this means the path forward will be simple. Skeptics within the physics community are right to point out that AI models are only as good as the data they're trained on, and superconductivity remains a phenomenon that isn't fully understood even after more than a century of study. Unconventional superconductors like UTe₂ demonstrate just how much remains mysterious, how effortlessly nature can still surprise even the most sophisticated theoretical frameworks physicists have developed. An AI system trained primarily on patterns from conventional, well-understood superconductors might struggle to predict something as strange as reentrant superconductivity under extreme magnetic fields, precisely because that kind of behavior doesn't fit neatly into the patterns the model has already learned. This is why the partnership between computational prediction and old-fashioned experimental physics remains so essential. Neither approach replaces the other. Together, they move faster than either one could alone. There's also a broader economic and geopolitical dimension to this race that's worth acknowledging. Nations and research institutions around the world recognize that whoever first develops a practical, scalable room temperature superconductor will hold an enormous strategic and economic advantage. It would reshape energy infrastructure, computing, transportation, and national power grids on a scale comparable to the transition from analog to digital electronics, or perhaps even more dramatic. That's part of why consortiums like SuperC operate as international collaborations rather than closed, secretive national programs, pooling expertise and computational resources from multiple countries in pursuit of a goal so ambitious that no single institution could realistically achieve it alone. It's also why funding for quantum materials research has grown so significantly in recent years. There's also something worth reflecting on about the nature of scientific discovery itself in this new era. For centuries, breakthroughs in material science have relied overwhelmingly on human intuition, decades of accumulated expertise, and quite often, sheer serendipity, stumbling onto something valuable while looking for something else entirely. Artificial intelligence doesn't replace that intuition and expertise, but it does something equally powerful. It expands the scope of what human researchers are capable of exploring in a single lifetime. A team of physicists, no matter how brilliant, cannot manually calculate the electronic properties of millions of hypothetical material combinations. But a well-trained AI system can process that scale of information, flagging the handful of candidates most likely to succeed, and letting the human experts focus their limited time and laboratory resources on testing only the most promising possibilities. This partnership between human expertise and computational power, rather than either one working alone, appears to be the real story here. And it may well define how major scientific breakthroughs happen across many fields in the years ahead, not just in superconductor research, but in drug discovery, battery technology, and countless other areas where the space of possible solutions is simply too vast for humans to search alone. As this research continues, expect to see AI-driven materials discovery accelerate even further. The models used by teams like the SuperC consortium will only get more sophisticated as they're trained on more data, including the results from experiments like the one that confirmed YRU-3b2 and LURU-3b2 as genuine superconductors. Every successful prediction, and every failed one, feeds back into the system, refining its understanding of which atomic arrangements are likely to produce the elusive electron pairing behavior that defines superconductivity. It's a virtuous cycle, one where computational predictions guide experimental synthesis, experimental results refine computational models, and the entire process compounds and accelerates over time. So is this the superconductor that shouldn't exist? The one that finally cracks the century-old puzzle of room temperature superconductivity wide open? Not yet, not exactly. What we're witnessing instead is something arguably more important, the emergence of a fundamentally new way of searching for it, one where artificial intelligence and quantum physics work hand in hand to illuminate a path through a search space so vast that human researchers alone could never hope to explore it in any reasonable amount of time. The materials confirmed so far are proof of concept, not the finish line. But every proof of concept in the history of science has been the first step towards something much bigger. The race toward room temperature superconductivity, a race that has spanned more than 100 years of human ingenuity, frustration, and persistence, just gained an entirely new kind of teammate, one that doesn't get tired, doesn't need to sleep, and can sift through possibilities at a scale no human mind ever could. Whether that teammate leads us to the finish line by 2033 remains to be seen, but for the first time in a very long time, physicists studying superconductivity sound genuinely, cautiously optimistic that the impossible dream might finally be within reach.